Fubini's theorem, which we'll see today, and Tonelli's theorem from last time before the exam. So if you want, you can hand this in any time before the exam in our market. But this is just an offer for you to practice this stuff. Last time we've defined integrals on product measurable spaces, and we've seen Tonelli's theorem, which allows us to compute the integral on such a product space as an iterated integral. So rather than integrating with respect to mu times nu, we can first integrate with respect to mu and then with respect to nu if the function we're integrating is non-negative. That was essentially what Tonelli's theorem said. So I'm going to write this down. So this is essentially what Tonelli's theorem said. Yeah, what I said, if we want to integrate, to compute the integral over a product space, we, if the function we're integrating is non-negative, we can just compute the iterated integral. So first with respect to one measure and then with respect to the other measure, and we get the same result. And in particular, the order of integration doesn't matter if we use this iterated integral. Well, but there was this restriction of non-negativity for the functions, and we've actually seen one counterexample where the function was not non-negative, where it could actually go wrong, right? We've had this function, I think, x squared minus y squared divided by x squared plus y squared. And for this function, we saw that the order of integration does matter. If we swap the x and y integrations, we got different results for the integral. So this showed that this non-negativity assumption in Tonelli's theorem was actually important. However, we can in fact do better than Tonelli's theorem, and that's Fubini's theorem, which we'll see now. So one can remove this non-negativity assumption if we add a different assumption. And that's called Fubini's theorem, and it goes like this. Let x, sigma x, mu and y, comma, sigma y, comma, mu be sigma finite measure spaces. And then if f is in L1 of x times y, comma, sigma x times sigma y, the product sigma algebra, comma, mu times mu, then the function that maps y to f of x comma y for fixed x is mu integrable for mu almost all x and the other way around, and the function that sends x to f of x comma y for fixed y is mu integrable for nu almost all y. Okay, so up to now this just says if we keep one variable fixed, then in the other variable it's integrable. At least almost everywhere. And now comes the important bit. The following formula holds: integral over x times y, f with respect to the product measure d mu times nu is the same as integral over x, integral over y, f of x, y, d mu of y, d mu of x. And we can also swap the integral. So this is the same as integral over y, integral over x, f of x, comma y, d mu of x, d mu of y. And all the integrals are well defined. Okay, and to prove this, the proof, if you do it carefully, it's rather long, and I'm only going to do a sketch. But essentially, it follows from Tonelli's theorem applied to the absolute value of f, which is non-negative. But first, let's take a moment and again compare this theorem to Tonelli's theorem. In Tonelli's theorem, as I said, one of the assumptions was non-negativity. That's missing in Fubini's theorem. So the function does not have to be non-negative. It could be anything. But on the other hand, in Tonelli's theorem, the function only had to be measurable, not integrable. So the integral could be infinite over the product space in Tonelli's theorem. In Fubini's theorem, however, f is assumed to be in L1 of the product space. So this integral with respect to the product measure here, this has to be finite. Or this, has to, exist. So this assumption is stronger in Fubini's theorem. And if we assume this, then we can drop this non-negativity assumption. So this is the difference between the two theorems, essentially. And if we have this, f in L1 of this product space, then we can swap integrations even if the function is possibly negative somewhere. Okay, so the two theorems together are quite powerful and have many interesting applications, as you will see on this problem sheet 11 that I made for you. So those who came later, there's an 11th problem sheet just for you to practice for the exam if you want to see some applications of these theorems. Okay, are there any questions before we start the proof of Fubini? So as I said, I'm only going to sketch the proof. So, okay, by assumption f is in L1 of this product space. So this implies that the integral over x times y over the absolute value of f, d mu times nu, is finite, right? When we talked about integrability, there was a remark that said f is integrable if and only if the integral of its absolute value is finite. So we have this. Okay, but now the absolute value of f is a non-negative function, so we can apply Tonelli, right? So by Tonelli, this integral is equal to the iterated integral, first with respect to mu and then with respect to nu, or the other way around, doesn't matter, right? So we can, but this is finite, so the iterated integrals also have to be finite. So integral x, integral y, absolute value of x, comma y, d mu of y, d mu of x is finite. Okay, and now we can, this inner integral, we can consider this inner integral as a function of x, right? And then this line here tells us that the x integral of this function of x is finite. And we've seen that if the integral of a function is finite, then the function itself must be finite almost everywhere. So from this line, we get that this inner integral with respect to y, integral y f of x, comma y d mu of y is finite for mu almost all x. Okay, so again, because the x integral of this is finite, this function as a function of x has to be finite almost everywhere. Okay, but now we can do, we can apply the same reasoning again to this integral, right? So for mu almost every x, this integral is finite, so this absolute value f of xy has to be finite for almost every y with respect to nu. So no, that doesn't really, it doesn't really matter, sorry. Forget what I just said. This integral must be finite for mu almost every x. This integral being finite is equivalent to f being integrable with respect to nu, right? Integrability just means integral over the absolute value is finite. So this already is equivalent to f of the function that sends y to f of x, comma y is nu integrable again for mu almost all x. Okay, so this is this is this statement, this first statement of Fubini, this integrability. And now to get this formula, we can just apply Tonelli to the positive part of x and the negative part of x, because these are non-negative functions. So again, Tonelli implies that integral over x times y f plus minus d mu times nu is the same as integral x integral y f plus minus d mu d mu. And I write this down because f plus minus are non-negative. Okay, so this formula holds for f plus and f minus, and then we just subtract f plus and f minus, and we get this formula for f. And that's essentially the proof. So to get the other formula with swapped integrals, you can just swap mu and u if you want. So by Tonelli, you can swap the integrals here, and that's the same thing, and then you get the swapped integrals in this equation. So this is essentially the proof. Yeah, and one thing that I skipped. So why is this only a sketch of a proof? For example, I didn't show that these functions are actually measurable functions, and so on. And some measurability of sets is missing in between the lines. But the key ideas how you get to this formula are contained in this proof. Namely, you take the absolute value, then it's non-negative, then we can apply Tonelli, and then we get this formula. Okay, and it nicely shows how the non-negativity assumption in Tonelli can be replaced by this integrability assumption in Fubini, because by integrability we can replace f by its absolute value, and we get a finite integral, and then we can apply Tonelli again. Okay, so again, Tonelli and Fubini are among the most important theorems of the entire lecture, and they're really, really, really useful. You can prove all kinds of stuff with them, and you'll see some of it on problem sheet 11, and some of it now-ish, maybe today, maybe on Friday. We're going to do a couple of examples on the blackboard. So are there any questions about Tonelli and Fubini before we continue? Okay, if not,
actually, I thought of a question.
yes.
So last time when we had an integral where we couldn't swap the integrals around, where does it fail with Fubini? Like the y minus x?
Yeah, that's a good question, and we'll come to that. So we will continue with this example. Yeah, in a minute. I'll do one remark, and then we'll talk about this example again. And yeah, that's a good question. That's remark 7.15. And this remark can be quite useful it just says how we can combine Fubini and Tonelli to show existence of integrals. So I said this already. Recall that f is integrable if and only if absolute value of f is integrable. Since the absolute value of f is non-negative, Tonelli applies. And we get the criterion that f is integrable on the product space, so in L1 of x times y, comma sigma x times sigma y, comma mu times mu, if and only if any of the following three conditions hold, either integral x times y, absolute value of f, d mu times nu is finite, or the iterated integral, integral x, integral y, absolute value f of x, y, d nu of y, d mu of x is finite. Or the other iterated integral is finite. So integral y, integral x, absolute value f of x, y, d mu of x, d nu of y is finite. So this is quite handy. If you have any function on the product space and you want to know whether it's integrable with respect to this product measure, then you can just take the absolute value, compute one of these iterated integrals, whichever you want, and if that's finite, then the function is integrable on the product space. So that's really a really convenient criterion for integrability. And then if any of this is finite, you can apply Fubini and you can swap the order of integration, and you know that these integrals over f are the same if you swap the x and y integrals. Yeah, so let's write this down. i.e. in order to apply Fubini, it suffices to check that this iterated integral over absolute value of f is finite. now we'll come back to this example from the beginning of the section and check why Fubini fails in this example. So so the measure space we're considering is R2 together with Borel sigma-algebra of R times Borel sigma-algebra of R, and the product of the Lebesgue measure with itself. Then I claim that the function that sends x comma y to y squared minus x squared divided by x squared plus y squared squared is not integrable with respect to this product measure. Over the square 0, 1 times 0, 1. Okay. Yeah, so intuitively, this function, if x and y are both 0, then the denominator becomes 0, so this function has a singularity at 0, which is included in this square. So this might be one reason why this function is not integrable. And that's kind of what goes wrong. Just to remind you, last time we started the section with this example, and we computed the two iterated integrals in x and in y. And then we swapped the order of integration, and we got different results. And then we wrote down the theorem of Tonelli, and we noted that Tonelli does not apply to this function, because this function can become negative because there's a minus sign in front of this x squared, basically. So Tonelli does not apply to this function. And now we're going to show that Fubini also does not apply to this function, which is as it should be, because otherwise the iterated integrals could be swapped, right? But they can't. We know that. So Fubini also does not apply, because it's not integrable over this square. Okay, and we're going to prove this. And the proof is a little bit dry, but essentially one shows that the singularity at 0 is so bad that if you take the absolute value of this function, then the absolute value is not integrable because it grows too fast at 0. Okay, and there's one trick to do this. So we have to take the absolute value and then bound this below by something which is large, right? So that we can show that the integral is infinite. And there's one trick. And the trick is to consider just a suitable subset of this square. The subset is this one. Let S be x comma y in 0, 1 times 0, 1, such that y over 4 is less than x is less than y over 2. So this set S looks like this. So if this is the square 0, 1 times 0, 1, then okay. Then on the left-hand side you have equality when y is equal to 4x, right? So that's a line that looks something like this. On the right-hand side you have equality when y is equal to 2x. So that's a straight line with a smaller slope. So the set S looks somewhat like this. And then if you have these two inequalities, then you can do estimates with this term. And in particular, you can get lower bounds. So on this set S, we have the following bounds: y squared minus x squared is larger or equal than y squared minus y squared over 4. That comes from this inequality. X is less than y over 2. So if we subtract this, then this becomes a larger or equal, and the y over 2 becomes a y squared over 4. So we have this inequality for the numerator of this fraction, and we also have x squared plus y squared is less than or equal to and here I guess we're using this. So are we? No, we're using this again. We can replace x by y over 2, so y squared over 4 plus y squared, which is 5 over 4 y squared. So we have these two inequalities on the set S. And now we integrate. Okay, so if we take the absolute value of this function, then we can apply Tonelli to compute this integral over the absolute value as an iterated integral. And it might be infinite. That's fine in the Tonelli case. So this integral is the same as the iterated integral, integral 0, 1, integral 0, 1 over the same function, y squared minus x squared divided by x squared plus y squared squared d m of x dm of y. And now we use these two inequalities. we can replace the numerator by this. By the way, this can be simplified, of course. This is 3/4 y squared. So we can replace the numerator by 3/4 y squared and the denominator by 5/4 y squared. And then we only make it smaller. So this is larger or equal than integral 0 to 1, integral 0 to 1. The characteristic function of s. Right, okay, so we're doing two things here. The first thing is this integral over the whole square is certainly larger than the integral just over s, right? Because the function is non-negative. So if we replace this integral by an integral just over s, we're only making it smaller. So that's the first thing we're doing. And then on s, we can replace the numerator by this and the denominator by that. Because on s, we have these inequalities. And again, we're only making it smaller. So this is what we're doing. So this characteristic function of s means we're only integrating over s. And now we replace the numerator and the denominator by these two terms. 3/4 y squared times the inverse of the square of x squared plus y squared. So 5/4 y squared to the power minus 2 dm of x dm of y. Okay, and now this can be simplified, of course. This is the same as, so these numbers 3/4 and 5/4 to the power minus 2, if you just combine those, you get 3/25 just as a constant factor. And then in the integral we have integral 0 to 1, 1 over y squared. That's what we have left, because there's a y squared here, and there's a y to the power minus 4 here. So y to the power minus 2 survives. And now this characteristic function of s, we can replace this by just integrating in x from y over 4 to y over 2. So, and on this domain, the characteristic function is just 1. Right, so in x we're integrating from 0 to 1, and in y we're integrating from here to here. So from this one boundary of s to the other boundary of s. Yeah, this should be right. And then, well, now this integral we can compute, right? That's just integral from y over 4 to y over 2 over the constant function 1. So that we can just compute as a Riemann integral if we like. So this is 3/25, integral 0 to 1, 1 over y squared, and then this integral gives us just y over 2 minus y over 4. Dm of y. difference is just y over 4, right? So this y cancels this square, so 1 over y is left, and we get an additional factor of 1 over 4 in front. So we get 3 divided by 100 now, because this 1 over 4 factor we can absorb in this prefactor, and then integral 0 to 1 1 over y dm of y. But we know that this integral is infinite, right? Because 1 over y has the singularity at 0, and the integral of this function is infinite. So we get infinity. So we've shown that the integral over the absolute value of this function is infinite, so the function is not integrable with respect to this product measure, as we claimed. And because it's not integrable with respect to the product measure, we cannot apply Fubini. So that's what goes wrong in this example. Are there any questions? Okay. Okay, so the next thing will be another example. Yeah, and also a word of caution. So this next example has nothing to do with Fubini or Tonelli's theorem, but is just about product Sigma-algebras. So the first example is one can show, and on problem sheet number 10, that's one of the exercises, one can show that the Borel sigma algebra of Rm times the Borel sigma algebra of Rn is in fact equal to the Borel sigma algebra of Rm plus n. So in the case of the Borel sigma algebra, this is quite nice, right? This is what one would expect. If you just increase the dimension, you can just as well take the product sigma algebra of these lower dimensional Borel sigma algebras, and you get the same thing. And in addition, if you take the Lebesgue measure on these sigma algebras, then the Lebesgue measure on this left-hand side, Borel sigma algebra of Rm plus n, is the same as the product measure, Lebesgue measure on this one, Borel sigma algebra of Rm, times Lebesgue measure on Borel sigma algebra of Rn. So this is also quite nice. So the Lebesgue measure really decomposes into the lower dimensional version of itself on this Borel sigma algebra. And in fact, one has even more. By the uniqueness lemma, the Lebesgue measure is the unique measure on the Borel sigma algebra of R n plus n such that m of a measurable rectangle A times B is the same as m of A times m of B. Because measurable rectangles are a pi system, and then you can apply the uniqueness lemma. This equation is slightly dangerous. So on the left-hand side, this is the Lebesgue measure on Rm plus n, and on the right-hand side, this is the Lebesgue measure on Rm, and this is the Lebesgue measure on Rn. So these are different Lebesgue measures. This holds for all measurable rectangles. So this was the Borel sigma algebra, and unfortunately things are less nice for the sigma algebra of Lebesgue measurable sets. In fact, one has the following: sigma L of Rm times sigma L of Rn is a proper subset of sigma L of R n plus n. And the proof that these are not equal is actually not too difficult. One can prove this as follows. So we know that the sigma algebra of Lebesgue measurable sets is complete, right? Every subset of a null set is measurable in this Lebesgue sigma algebra. And one can show that this left-hand side is not complete. So the right-hand side and the left-hand side must be different. And to show that this left-hand side is not complete, you can just do the following. You take a non-Lebesgue measurable set in Rm, and consider, for example, the following set.